the dust, he says. Okay, Isaiah 29. Now, could these, we're going to look inside. Now, these, inside you saw the little spheres. They turned out to be iron rich. And the first question is, could this just be melted steel? I pointed out you don't expect steel to melt in fires with kerosene or paper, office materials. And indeed, NIST, one of the head scientists, said your gut reaction would be jet fuel made the fire so very hot. A lot of people figured that's what melted the steel. Indeed, it did not. The steel did not melt. The temperatures of these fires in the towers would be, could approach 1,000 degrees, yes, but steel, centigrade, but steel melts at 1538, plus or minus a little, centigrade. So you're nowhere near enough, hot enough. And as Professor Eager also pointed out, the temperature was not unusual in the WTC, most definitely not capable of melting steel, and that we agree. So we're going to look now using an electron microscope with a microprobe. Here's the electron microscope. And we see the image on a screen. We're going to go in now and look at this dust. First, I want to show you what steel looks like. This is going to be our main question. Oh, and we'll look for a peek at aluminum, too, in these little... I mean, is it pure aluminum? Now, aluminum... Well, we'll talk about aluminum later. Remember, aluminum is in thermite. So, you know, you expect to see some aluminum, and you also expect to see iron in thermite. And if it's thermate, you also expect to see... Good. Sulfur. Steel that was melted with an oxyacetylene torch is mostly iron, quite a bit of oxygen because as you do get droplets of steel with an oxyacetylene torch. And I collected some of these. Now we're looking at one with X-EDS analysis. And you see iron, that's the main peak here. A little bit of manganese, which is in steel. Here's another iron peak. So see, iron gives you these peaks. Now, what is going on? What generates these peaks? Well, the electron goes into the material that you're analyzing, and it excites the atoms, gets them all revved up, and then they emit X-rays of a characteristic wavelength, or energy is what we're looking at here. And so it's like interrogating, asking, without damaging, by the way. The electrons go in, excite the atoms, and then individual elements will emit a characteristic pattern of X-rays. So with iron, you see these three peaks. And you say, aha, there's iron. And the analysis code then tells you approximately how much. About 60% in this one. A lot of oxygen because it flew through the air, and some carbon. The carbon we have to be a little careful about. I put that in parentheses because I'm using carbon tape. These little spheres are adhering now to carbon tape. That's how I keep them from moving around. So carbon is not as reliable. There's a little carbon in steel, however. So this is a very simple pattern. Essentially iron, a little bit of manganese, and then because it was melted at high temperature, we have the oxidation there. Oxyacetylene torch, by the way, is what they use to cut through the steel at World Trade Center. So it is important to check to see if these droplets are steel. Now, thermate also forms flow, as you see, but also tiny spheres. If you look closely, there are little sparks coming off. Those sparks tend to form spheres. Now, why is it that a molten material forms into a sphere when you throw it through the air? Surface tension, great. Just like water, right? Raindrop. You get the surface tension, forms it into a drop. Now this iron, plus whatever else, like sulfur, aluminum, you will form a sphere because it's hot, and then it has surface tension, pulls it into a ball, and then as it flows through the air, it cools off and retains that spherical character. Now, this is just with a camera, with macro, and you can see, you kind of see some spheres. It's much. This is 1 millimeter, so these spheres tend to be small from thermate. This is looking now with the electron microscope. You see these spherules. I'm just going to call them spheres or microspheres. Here's the scale, 1 millimeter. So you see we do get some close, and then right on down to a few microns. That's what you get from thermate and thermite. You get that as well. Here's the thermate signature as seen in the electron microscope system. This is called an EDS plot, or X-EDS, or EDX. A lot we use different terms, but I'm going to stick with X-EDS. X-ray, this will be on the test also. X-ray, Energy Dispersive Spectroscopy. Okay, so we're looking as a function of energy down here, KeV. But the important thing is the peaks. This is in thermate now. We see iron, little manganese maybe, not much. No, really not much to write home about. Sulfur and aluminum. So that's the signature. Iron, sulfur, aluminum for thermate. For thermite, it would be iron, aluminum. Now this is an unusual mix. You don't have that much aluminum, and certainly not that much sulfur in steel. Sulfur makes steel brittle. So, and as I pointed out, that steel sample, by the way, was from the World Trade Center. That was a little sample of steel that was left over from a monument, and we were able to get a small piece of that. You don't see the sulfur or aluminum there in these quantities, certainly in the World Trade Center steel. Now we're going to look at our first sphere from the World Trade Center dust. This sphere was the one that caught my eye. And there were actually 3 droplets that caught my eye. And I saw this in January. You know, I admit, I should have thought of this sooner. I'd seen thermite go off. I'd seen the little spheres that thermate makes when you do an experiment. We gathered some of those up. You know, I should have looked in the dust sooner. But it took looking at the dust again in January, and I saw these 2 or 3 objects right there, big enough to see with my naked eye. It was like someone's clubbing me over the head. Look at this stuff. Of course, I was very excited to see it. I thought, wow, I got to see what's inside this. Melted. That means it was molten at one point. If it's got iron in there, that's very high temperatures, higher than the fires can reach. So what is inside this? Maybe it is just pure aluminum, though, you know, from the jet, somehow forming into droplets. We're going to look. Drum roll. Here we go. Okay. One of these is from the World Trade Center dust, that sphere that I just showed you. One of these plots is from thermate, which so one is just the X-EDS signature for thermate. Now I ask you, which one is which? This data has never been shown before. These data, I should say, data is plural. And is that something? I must admit, I lost sleep when I first saw Building 7 come down and did the timing on it, because I thought, man, this is a smoking gun for somebody getting into this building, never hit by a jet, you know, it looked so much like a controlled demolition. But now we have what I consider another smoking gun. I think, Alex, you used that term as we discussed this on the radio. And now you can see the plot. Can you see that iron? It's very clear. Sulfur and aluminum. That's the signature for thermate. Iron, sulfur, aluminum. Folks, you really, there are some differences, but you can't tell which one is which, can you? I mean, they have the same, the signature for thermate is there. And this, by the way, this method is what is used by investigators when they're looking for thermite, or if you have sulfur, thermate residue. They use this same EDS method. Energy Dispersive Spectroscopy. There you have it. So you want to know